So let's see. The problem that, and I'm going to again remind you, basically we can solve one of the two, minimization or maximization. So I'm going to do this basically minimization of, say, some integral a to b, and call this L, right? And L should remind you, basically, once we know how to do unconstrained optimization, putting this lambda is more than enough, right? And then we'll get there in, a little bit later. So L of x comma x dot and dt, right? And with the independent variable, I'm choosing it to be time here, but I could have probably chosen something like L of f comma f prime and dx or something like that. I mean, very well. I mean, x could be independent variable, f are the functions that we are looking for. Derivative with respect to f also impacts your objective function and things like that. And then why stop at first derivative? You can actually go for higher derivatives and things like that. But we know this state space technique. Even if you have higher order stuff, we can always convert it back to first order things, right? So by defining vector functions rather than scalars, right? So anyway, we will simply look at this particular problem and see what happens, right? For the time being, in my mind, I'm looking at unconstrained optimization problem. And hopefully you remember basically the technique that we did. Let's basically assume that x bar of t is the local minimum. Okay, what do we mean by local minimum? So in other words, integral 0 to a to b of this Lagrangian over this function, okay, which has a derivative hopefully, dt is less than or equal to a to b of the Lagrangian x comma x dot dt for all x minus x bar norm is less than some small number epsilon or something like that. Except basically this norm is defined over the function space, right? If you remember, this could be defined as perhaps square root of integral of a to b x minus x bar whole square dt raised to half, right? There could be many other ways of doing it. So what we did after this particular step, we actually approximated using Taylor series, and then basically we're going to do that. So when I approximate this with Taylor series, I'm going to get something like partial of x with respect to sorry, let me L of x bar plus x bar dot plus partial of L with respect to x times x minus x bar plus partial of x with respect to x bar times x dot, sorry, this is x bar dot, comma x minus x bar dot, okay, plus higher order terms. Okay, so now what is x minus x bar? For the time being, let's define some eta of t to be that x minus x bar, x of t minus x bar of t. Okay, so therefore L of x comma x dot is basically L of x bar comma x bar dot plus eta of time times partial with respect to x plus eta dot of t partial L with respect to x dot, both evaluated at x bar, right? Okay, x bar and x bar dot, x bar dot. Okay, so this eta is like the perturbation that we did from the optimal and things like that. So now where are we going? So go back to the integral a to b L of x bar comma x bar dot dt is less than or equal to integral of all this, right? So in other words, 0 is less than or equal to integral of this partial with respect to x times eta, okay, plus partial of L with respect to x dot eta dot, okay, and dt. And this is true for all kinds of perturbations around that ball, around x bar. One of the things that we need to notice is eta and eta dot are not independent. One is a derivative of the other, so we have to do this particular trick, which I'll show in a second. A to b of this partial with respect to x dot eta dot, by doing integration by parts, we will get something like AB minus A to B d by dt of partial with respect to x dot eta of t dt. Okay, so substituting all that, I'm going to get basically partial with respect to x dot eta AB plus this complex looking thing, partial with respect to x minus d by dt of partial with respect to x dot times eta of t dt. Okay, so I will conveniently assume that this is going to be 0, and it's quite appropriate if we actually say that I know exactly what should be the value of x of a and x of b when they're fixed. Then basically any perturbation that satisfies those two constraints, x minus x bar will also be 0 at each of these 2 points. So that's how I concluded that this has to be 0. You could have actually one of them flexible and things like that, and that will lead to a slightly more complex problem, right? So what that gives us eventually as basically 0 should be greater than or equal to this thing. I'm going to simplify notation, Lx minus Lx dot dot. Okay, I mean that's not the way to define it, but I'm being lazy and then just writing it that way. Okay, now this is true for all eta t. Okay, and in a ball around x bar, eta to t, let's say if eta t belongs to that, minus of eta t also should be there. So therefore you have again a quantity, an integral which is greater than or equal to 0 for all eta, whether they are negative or positive in a function sense. And it's not that tricky, but slightly subtle. This will actually imply, as you may guess, I'm going to write this carefully. Partial of L with respect to x evaluated at x bar comma x bar dot minus d by dt of partial of L with respect to x dot, okay, evaluated at x bar comma x bar dot. So that should go in, okay, and this has to be equal to 0. Okay, and this is very famous. It's called Euler-Lagrange equation, and this is some beautiful history. Maybe I should share some of the history behind some of these problems. There are many problems that belong to this category. There problem that we discussed from Dido is, from the ancient, and we people rediscovered and then thought of that as a functional optimization problem much later. But one of the first problems that come to mind in the functional optimization problem is the so-called Snell's law, without solving it as a calculus of variation problem. The Snell's law is basically, let's say if you have one point and another point and you want to send light, and then you have two media. We know that it refracts based on the refractive index of either sides, but refractive index has everything to do with the speed of the light in each of this medium, and then basically Snell's law says that it will take a path, right? It will take a path that will be the shortest path, right? It may not, it won't look like a curve and things like that, because this will take a long time, right? So that's the Snell's law stated as a physics law, and then from mathematics we can actually show that this is going to be straight lines and things like that. You can imagine in a slightly different way, basically if you had a cross river and part of the land and things like that, and those 2 points are aligned like that, then which point do you cross the river and which angle you take and things like that. Again, you will see that you may have actually straight line on the line, but on the other hand you may have actually curves, simply because the flow of the water could be different in different places and things like that. So all such problems were thought about before one interesting problem called Brachistochrone problem, stated by none other than Johann Bernoulli. And the problem is basically, if I have to create a wire so that one bead goes from this point to this point in the shortest possible time, and then typical guess would be that it has to be a straight line, but if you forget about gravity, that may be an answer, but the gravity is there, and then basically the answer is certainly not a straight line. And this was posed openly to everybody, and a bunch of people submitted answers anonymously. And in fact, the first person who submitted happened to be Isaac Newton. So Isaac Newton not only invented calculus, he solved one of the first problems of calculus of variations. Certainly Johann Bernoulli solved, and his brother Jakob Bernoulli solved the same problem. Euler solved for sure, and few others. Leibniz was one of them. So the problems stated by Johann Bernoulli was solved by bunch of great people at that particular point, and eventually Euler gave this particular condition, and his approach of proof was the discretization approach apparently, and then basically eventually Lagrange, when he was in early 20s, submitted this solution based on purely analytical methods, and Euler and Lagrange became acquainted and probably friends at that particular point, and Euler, if I'm not mistaken, gave a prize to Lagrange for that particular solution. So that's why it's called celebrated Euler-Lagrange equation, which is quite powerful. So let's actually go back to, so if you have a constraint, then that essentially you put a lambda and things like that. Let's talk a little bit about constraints. So if you had a constraint, something like in our case, what was that, r of theta d theta is equal to L, right? So this is an integral constraint, what we call it as an integral constraint. So, and then for which basically it's a single constraint, right? And then you pick one Lagrange multiplier and we are done with it. So our Lagrangian for let's solve this. So r is our function, comma lambda is simply going to be the lambda is a real number here, 0 to 2 pi. Okay, and if you recall, basically it was half r square of theta plus r theta. Okay, but what about this L? L should also get into integral, but this can be seen as basically integral 0 to 2 pi L over 2 pi d theta. So I can write this as L over 2 pi and this whole thing multiplied by your lambda, the multiplier. Okay, so let's recall this is nothing but partial with respect to r minus d by d theta. Theta is the independent variable here. Partial with respect to r dot, and this has to be 0, right? R prime, or dot, whatever. Since we're not dealing with time here, r prime would be appropriate. But the function itself is not dependent on r prime, so this part is actually 0. So partial with respect to r has to be 0, and then that essentially says that r of theta, okay, and then the second part is basically going to produce lambda. So plus lambda has to be equal to 0. So in other words, this tells me r of theta is going to be some constant lambda. Lambda could be positive or negative. But then we have a constraint equation that says 0 to 2 pi r of theta d theta is equal to L, which is essentially going to be minus lambda d theta. So therefore lambda is going to be equal to minus L by 2 pi. Okay, and then r is going to be L by 2 pi, which we know to be the circle with perimeter L is equal to 2 pi r, and the corresponding area we can compute is going to be pi r square, or pi L square by 4 pi square simplifies to L square by 4 pi, right? So this is the solution to maximization of a string with a particular length, the maximization of the area that it can enclose, right? So and then we use this Euler-Lagrange equation. This is a quite straightforward equation, and then we kind of jump to basically constraint optimization, without really considering many aspects. So let me maybe show a couple of other examples. We don't necessarily show the complete solution, but it will shed some insights into this, right? So these are unconstrained problems. Basically we have something like 0 to 1. So let's call this as y comma y prime, okay, and y prime square of x, let's say 1 minus y prime square of x and dx, right? So our Euler-Lagrange equation is basically we have to satisfy partial of L with respect to x minus d by dx, sorry, this has to be y, d by dx of partial of L with respect to y prime, right, all evaluated at some optimal value, has to be 0, right? So but in this particular case, again, this is 0, right? So in that sense, this this has to be constant function with respect to x, but partial of L with respect to y itself is going to be a function of y prime, and that function is going to be 2y prime times 1 minus y prime minus 2y prime cube, right, y prime square. And this is going to be a constant function, basically. So let me manipulate this. 2y prime minus 4y prime cube is some function of, I don't know, call that q or something like that, some function of x, right? Sorry, some constant. It's not a function of x. D by dx of something is 0, so it's a constant with respect to x. So this is a differential equation that we haven't seen so far. It's a cubic differential equation. It's, there are many some methods to solve, and they're not easy to solve, right? Of course, this is equal to constant, so perhaps you can guess that y prime may be a constant, and then therefore y is going to be a linear function and things like that, and then solve this problem in that sense. But otherwise, finding the Euler-Lagrange equations will give you some equation, typically a differential equation, and we struggle to solve those differential equations, right? So interestingly, what do you call that? If you have Lagrange multipliers, in certain cases, they will give Lagrange also another differential equation. Where do we get that? Let's go back to our Euler-Lagrange equation and then look at it. So you see this partial with respect to x and so on and so forth. So if this had lambda, right, and let's say for the time being that lambda is also time dependent, why that is the case we'll come in a second, then basically by taking this d by dt will produce another differential equation in lambda. So you will have differential equation x as well as lambda. So you'll have this very complex set of differential equations that need to be solved, and you know, in that sense it's a nightmare. And then basically many times with powerful computers perhaps the discretization approach is better, or of course, you know, these differential equations themselves can be solved using discretization, and we will look at that carefully when we do optimization from a controls perspective, the optimal control perspective, right? So the last thing that I want to say before we close this particular lecture is the constraints. Sometimes basically we saw in our previous problem basically something like r of theta d theta is equal to L. So this is one single constraint, right? Some integral value has to be equal to 1. But on the other hand, sometimes we may actually have something like r theta plus r dot theta is equal to 0. Okay, for some reason I'm going to assume that. Okay, now this one has to be true for all theta. So how many constraints are there? In reality, you have infinite number of constraints, you know, arguably uncountably infinite, right? So for such cases, basically we would have to have something like 0 to 2 pi and lambda of theta times r of theta plus r dot of theta. This is the part that's going to go into the Lagrangian, right? So where this lambda becomes dependent on theta, because it kind of you know, for every theta you'll have a lambda value. So it's like Lagrange function, you know, Lagrange multiplier function. So if, you know, the pattern is very clear. If you have a single constraint, you'll have lambda. If you have say 2 constraints, you'll have 2 lambdas, you know, 2 lambda 1 lambda 2 or whatever you want to call. And if you have infinite number of them, you'll have lambda 1 lambda sequence. If you have uncountable number of constraints, as is the case in a functional equation, you'll have a function which is obviously like a uncountably infinite number of Lagrange multipliers, right? So depending on what type of constraint, we'll either have to choose that is a function of lambda, or as in the previous case, if it is a single constraint, we will take the Lagrange multiplier to be, you know, a scalar, a real number, not a function. Okay, so anyway, we will see some of these aspects again in optimal control lecture next class. Hopefully you understand how these calculus of variations are going to come. But the key thing is, let me go back and show you the understanding is basically we use the same technique. We use the same idea, right? We use the what do you call Taylor series expansion, except basically since we are dealing with functions and things like that, we have to be careful, and therefore we have these partial derivatives with respect to those, you know, functions seemingly treated as constants, and then basically you know, the perturbations that are also functions, but otherwise it's the same idea, right? But here, unlike any of the previous examples, basically this perturbation and this perturbation are you know, together, in the sense that this is a derivative of this. So we have to use this integration by part idea, and we'll get this additional term, and then this has to be 0. Now in some cases this is not going to be 0, simply because these a and b are not constrained to be constants, you know, not known and things like that. So we have to be smart in terms of picking the right set of conditions. But in all such things we can actually pick, you know, something independent here, something independent here, and then we'll get bunch of conditions, right? So but otherwise the idea is the same, and you know, use essentially Taylor series to show the derivatives to be 0. So this is like your first order necessary condition, right? It's may look very, very different and complicated, but this is the first order necessary condition. Do we have second order necessary conditions and sufficient conditions after that? Yes, right? There's no doubt, and it's going to get a lot more complicated, especially in the constrained case. In the unconstrained case, it looks relatively simple. It looks like the Hessian being positive definite or non-negative definite. It will look something like that. But if you're talking about Lagrangian, then it will look a lot more complicated, because the tangent plane itself is now very difficult to even imagine and things like that, right? So most of the time we basically hope that this first order equation will provide a small enough number of solutions over which we can actually try out and compute the values of these things, and we'll give an answer. But be careful. This first order conditions never give you either their maximum or saddle points or minimum and things like that. So one has to be very careful. It may give maximum or minimum, like in the example we have seen earlier. Okay, but this approach has a lot of history behind that. Brachistochrone is one of the simplest things that one can think of in this particular type of problem. There are many other problems that people solved over the years, but what eventually made this, how do I put, indispensable is basically the connection to mechanics. And Lagrange and Euler both worked quite a bit on mechanics, and Lagrange, along with later scientist Hamilton, changed the entire understanding or formulation the way Newton did, versus gave a very theoretical flavor, beautiful flavor to mechanics. And everywhere basically you'll get this Euler-Lagrange equation. And some of you may have gone through courses on Hamiltonian mechanics or Lagrange mechanics and would relate to this particular thing. Essentially what they surmised is basically perhaps Newton's law is a result of some minimization of some kind of function, objective function, and then that principle eventually became something called principle of least action. Unfortunately, it's not quite appropriate to call it least action, because it's not always the least, it's just an extremum. Something much more complicated than what I'm just pretending here. But essentially one can derive models for any physical system, whether it's mechanical, electrical, and things like that, but by associating some kind of potential energy, kinetic energy, and other types of things, and put this in Lagrangian formulation, we'll get this action kind of integral, and then pick the least action answer, and then that will satisfy this Euler-Lagrange equation, and that will give you the model. And then interestingly, that eventually extends to quantum mechanics in a very different way, right? So with that we will stop this long lecture, but hopefully this gives you an idea how functional optimization can be done. And next time we come, basically we'll make a point that optimal control is a functional optimization problem, and we will use this Euler-Lagrange equation to actually solve that particular problem. But it has it's one way, if you look at it, it's a special case of calculus variations. Another way of looking at it is a generalization. Both views are appropriate, and we will take one of the views and then basically derive some interesting solutions to optimal control problems. Thank you.